So, hello and welcome to this video lecture. So, this video lecture continues from the last one where we actually spoke about physically unclonable functions and how they could possibly be used for authentication and for other security aspects. Especially they would be important for lightweight devices like edge devices that are used in IoT. We also mentioned that there were two types of very commonly used puffs. One was the Arbiter puff and the other was the Ring Oscillator puff. So, in this lecture we will continue from where we stopped. We will look more in detail about the Ring Oscillator and Arbiter puffs. We will compare the two of them and then we will actually see how we could build authentication schemes, what are the current drawbacks of puffs and how potentially they can be mitigated. So, recollect that we actually looked at a Ring Oscillator puff which was something like this. So, there were a series of ring oscillators. Over here we had n oscillators and each ring oscillator had in this figure at least has 3 inverter gates, and the output of the third one is actually looped back and connected to the first inverter. Now, we have all of these ring oscillator outputs connected to multiplexers. So, this is shown as 2 n by 2 bit multiplexers, but we can actually have them as an n bit multiplexer, and then you have counters and a response which is of 1 bit. The ring oscillator puff works something like this. To actually start the ring oscillator puff, the user would have to give an enable signal, essentially change the enable from 0 to 1 and also specify a challenge. So, a challenge over here would essentially pick choose 2 ring oscillators out of the n oscillators. So, out of the n ring oscillators present, the challenge would essentially pick 2 of them. For example, let us say for discussion it picks say the ring oscillator 2 and ring oscillator n. Now, as we know, when the enable signal is 1, there is an initial state of the puff which gets fed back, and as a result there is a square waveform which gets present at the output of the puff. As discussed in the previous lecture, the frequency of this waveform is a function of these manufacturing process of this puff. So, for example, we mentioned that there is a capacitance that is involved, there is the threshold voltage and various other nanoscale aspects that could actually change the frequency of the ring oscillator puff. Therefore, what is expected that each of these n ring oscillators would produce a frequency that is different. Now, as we mentioned, what is done is that the challenge would actually pick 2 ring oscillators at random. So, we had considered in our discussion the ring oscillator 2 and n, and because of these intrinsic properties, the frequency of the waveform generated by the ring oscillators 2 and n would be different. Now, what is done over here is that there is a multiplexer to multiplex the ring oscillator 2 and the ring oscillator n. Therefore, what we obtain is R A and R B, both are square waveforms. One is this R A is due to this ring oscillator 2 and the multiplexer which has switched the second ring oscillator into its output, and this multiplexer has switched the nth ring oscillator to RB. Now, we have 2 counters, both the counters start with 0 and they begin counting each periodic or each positive pulse that is obtained from the ring oscillator. So, therefore, what we know is that since the 2 ring oscillators are operating at different frequencies due to their intrinsic properties, these 2 counters would, after a period of time, say like 1 or 2 seconds, would obtain a different count value. Now, based on this, we would make a comparison after say 1 or 2 seconds and determine which of these 2 counters is higher, and according to that we would give an output of 1 or 0. So, the response to the challenge is 1 or 0. In our example, if the frequency F A corresponding to this counter has a higher value, then we provide an output 1, else we provide an output 0. What we see over here is that the hardware device would implement this ring oscillator puff, and later when deployed, the an application could enable this ring oscillator puff, choose a challenge, essentially choose a pair of these ring oscillators, provide an output which is either 1 or 0. Now, the entire purpose of this ring oscillator puff, or the entire uniqueness of this ring oscillator puff, as mentioned in the previous video, is that this output response is going to be a function of that particular device. If I have two exactly identical devices, each of these devices having a ring oscillator puff, each would give me a different response for a particular challenge. So, what is done is that this one challenge gives me 1 bit of response. So, if we actually run this ring oscillator with multiple different challenges, we could build a larger output response. So, for example, if I continuously choose different challenges, I would get a larger string of responses. Each response is independent of the other. So, we will take an example and we will actually look at the various properties of the ring oscillator puff. So, we will be referring to this particular paper which was by Professor Devdas in DAC 2007. So, this paper shows the implementation of a ring oscillator puff vertex 4 FPGA. So, they compared 15 such devices. All of these devices are exactly identical, and they implemented 1024 ring oscillators in each FPGA. This means that the N over there was 1024. Further, they also used that instead of 3 inverters, they had used 5 inverters. So, each ring oscillator had 5 inverters and an AND gate. This particular figure shows the inter-chip variation or the uniqueness of the puff. The uniqueness of the puff response. For a given challenge, the same challenge sent to the device A and another device B, the responses are collected and the Hamming distance between the two responses is computed. This particular graph shows the response for 128 bits. Now, what is expected is that for a good puff, the inter-chip variation should be maximum. So, this means that the response of A should be as different as possible from the response of B. So, if you are considering that each response is of 128 bits, in order to have the maximum difference between the response of A and B, ideally the A and B should vary in 64 bits, and as we see over here on the x axis, it shows the Hamming distance between A and B, and the y axis shows the probability. We see that in a large this waveform for this distribution of the Hamming distance is around having an average of 59.1. So, ideally it should have been 64, but 59.1 is also a very good Hamming distance. Another check which we have also required was the intra-chip variation. So, as we mentioned in the previous lecture, the intra-chip variations shows the reproducibility or the robustness of a puff. So, as we mentioned, we provide the same challenge to the device which is having the puff, obtain the response, and in a different condition, maybe after a day or after a month or after a year, we send exactly the same device and obtain the response. So, we could also have different aspects, like we could send one challenge at a specific temperature, say 20 degrees, and with a voltage of 1.2 volts, and the other challenge to exactly the same device at which was heated to 120 degrees and having a voltage of 1.08 volts in this particular example. So, what is expected for a good puff is that independent of these environmental conditions like temperature, time, and input voltage, the response should be as close as possible for the same challenge. This particular graph shows the distribution of the intra-chip Hamming distance variations. So, it tells you how different each response looks for the same challenge under these two conditions, 20 degrees 1.2 volts, and when the challenge was given at 120 degrees 1.0208 volts. So, what you see is that in most cases it is most likely that the response does not change with the different environmental conditions. So, on average there was 0.61 bits of variation out of the 128 bits of the puff responses that were actually reported. So, we will now look at a different kind of puff. So, this is known as an Arbiter puff, and essentially this has certain different properties compared to the ring oscillator puff that we have seen. So, an Arbiter puff fundamentally is based on a switch. So, it has two multiplexers which is used in the switch. If you consider this particular figure, both are given the same input, that is 0 over here, and the same 0 is connected to this as well. And each of these multiplexers does is that based on its input either 0 or 1, it will switch that corresponding input to the output. So, for example, if the multiplexer select line is 0, then this input at the multiplexer is sent to the output. On the other hand, if the select line of the multiplexer is set to 1, then the input present at the second input, that is this input, would be switched at the output. Now, in an arbiter switch, two multiplexers are used. The same input is switched to both multiplexers present, and both multiplexers have the same select line. There is a minor difference between the two multiplexers, and what you see is that the input line is actually connected differently in each multiplexer. For example, over here the blue line is connected to 0 in this multiplexer, and therefore will be switched to the output when the select line is 0, while in this case the blue line is connected to 1. Similarly, the red line is connected to 1 in this case and 0 in this particular multiplexer, and therefore when the select line is 0, it is the red line that gets switched. So, what you see is, given this particular configuration of the switch, the output would be dependent on the select line. If the select line is 0, then we have the blue line on top over here and the red line at the bottom. On the other hand, if the select line is set to 1, then it is the red line which goes on top, or and the blue line which is at the bottom. So, essentially what this means is that depending on the select line, we are either sending the blue line or the red line in each of the multiplexers output. So, this primitive component called the arbiter switch is then used to build an arbiter puff. So, now the fundamental feature about this particular switch that makes it interesting for the arbiter puff is that these output, whether the blue is sent up on top or the red is sent on top, depends on the characteristics of these puffs. So, this fundamental arbiter switch is used to build an arbiter puff. A typical arbiter puff looks something like this. So, we have actually multiple such switches present one after the other, and a single input which is fed to both switches, to each switch as shown in the previous slide. So, we also have a challenge which is present. So, we have challenges which is 0 or 1, and essentially what the challenge does is that it decides whether the blue line or the red line should be switched on top and bottom respectively. So, over here for example, you see that we have put 0 for this particular switch, and therefore it switches the blue line to the bottom and the red line on top, and so on. After a series of such switches, we eventually have a flip flop. This is a D flip flop. This particular D flip flop gives an output of 1 or 0. So, there are essentially two aspects that makes this design interesting for use as a puff. The first is the fact that these signals, since they are propagating through all of these switches, due to the nanoscale variations in the design of these switches, these two lines, the red and the blue line, would attain a different speed of transmission. As we seen with the case of the ring oscillator as well, the delays provided by each of these multiplexers is influenced by the manufacturing processes and the various intrinsic properties of the silicon and the process as well. So, as a result, after cascading through a number of such switches, what we get is that one of these lines, either the blue or the red line, would reach the output faster than the other line. So, we also now have a D flip flop over here, which measures which of these two lines is in fact faster, and correspondingly gives a output of either 0 or 1. So, let us look in more detail about how this D flip flop actually is able to identify which of these two signals is indeed faster. So, let us consider a D flip flop, and what is done is that one of the lines, let us say the blue line is connected to the D input, and the red line is connected to the clock input, and the output is 1 bit, which will give you either a 0 or a 1. Now, let us say that the blue line, which is connected to the D input, reaches first. As a result, we would have something which looks like this. So, we have the D line reaching first and then the clock signal reaching, and as we know how a D flip flop works, when the clock transitions from 0 to 1, the input at the D is then latched at the output. Since the signal at the D line has arrived first, when the clock transitions from 0 to 1, the output would obtain a value of 1. On the other hand, if the clock in fact has arrived first, when the clock transitions from 0 to 1, it would see that the D is still at a value of 0, and therefore, the output Q would obtain a value of 0. So, thus we see over here that providing a rising edge, a 0 to 1 transition through these various switches would result in a differential path for these two lines, and as a result, at the output at this particular point, we have one path which is faster than the other. Now, as we have seen, the D flip flop, which is configured in this in the way that we have discussed, would be able to identify which of these two paths has arrived first, and correspondingly will be able to switch between 0 and 1. So, the challenge in the Arbiter PUF is the select lines of the multiplexers. So, for example, over here, considering that there are 3 switches, the challenge is 0, 0 and 1. So, note that if we change the challenge, it essentially changes the path for the red and blue signals, and as a result the output may change. Since the path is different, the choice between which of these two signals is faster may also be different, and therefore, the output of the puff would also change. So, creating an Arbiter PUF would require that we provide a challenge and correspondingly determine whether the output is 0 and 1. So, the uniqueness is obtained because each of these paths for a given challenge would be different for each device, and therefore, on one device the same Arbiter PUF for the same challenge would perhaps give an output of 0, while on another device would give an output of 1. So, this is essentially utilized for authentication and other purposes. So, this is a result for an Arbiter PUF. It is obtained from this particular paper, 2008 paper, which shows both the inter and the intra-chip distances at 2 temperatures. One is at 25 degrees and the other one is at 85 degrees. Okay, so, the results are quite similar to that of the ring oscillator PUF. So, what we see is that the inter-chip distance for the same challenge is having an average which is around 64 for a 128-bit response. So, this means that if I provide the same challenge to 2 different Arbiter PUFs, the response would vary by roughly 64 bits. Similarly, the intra-chip distance is less than 16 for a 128-bit response, and it's both cases the temperature does not affect the response much. So, what this means is that if I provide the same challenge to the same device with different conditions like a change of time, change of temperature or after a long time and so on, the response is very much similar. So, what we have seen are two puffs, the ring oscillator puff and the arbiter puff, and what we will see now is we will actually try to compare the two of them and see what are the characteristics of the two. So, the first thing to note is that in the ring oscillator puff we have these two multiplexers here and an n bit challenge. So, essentially the n bit challenge is choosing a pair of these two ring oscillators, and therefore, the number of challenges possible is n choose 2. On the other hand, the arbiter puff, we are essentially using the select line to choose a challenge, and if there are n such switches which are arbiter switches which are present, then the number of challenges possible is 2 power n. Therefore, the number of possible challenges for the arbiter puff is 2 power n. So, based on the number of challenges, we categorize these puffs as a weak puff because it has a very small set of challenges. In fact, the challenges are linearly dependent on the number of ring oscillators, or the strong puff in case of arbiter, because the number of challenges that are possible are exponentially related to the number of arbiter switches that are present. So, these are the properties of weak puffs. First of all, it has been noticed that weak puffs have very good inter and intra differences. There are comparatively few challenge response pairs as we seen in the ring oscillator, and because of this reason the CRPs or the challenge response pairs have to be kept secret and cannot be exposed to the attacker, because the number of such CRPs are very less. So, essentially weak puffs are used for creating cryptographic keys. They are used together with other encryption schemes, like they are typically not used by itself, but typically combined with other cryptographic schemes like encryption or HMAC and so on, in order to hide the CRP. So, note that the problem with the weak puff is that because the number of different challenges are limited, the attacker may be able to enumerate all of these challenges, and for each device the attacker could be able to create a database of all challenge response pairs, and therefore, without even having the device, the attacker would be able to provide a response from his database for any given challenge. Therefore, weak puffs have a limited application. Now, strong puffs, as we have seen, has a huge number of challenge response pairs. In fact, we have seen that there is the exponential number of challenge response pairs based on the number of arbiter switches present in the arbiter puff, and it is also assumed that because of this, the attacker will not be able to capture all the challenge response pairs, or the attacker will not be able to build a database of all these challenge response pairs. Therefore, the used challenge response pairs can be made public, and typically these strong puffs will not require a cryptographic scheme because there is nothing secret which needs to be stored. So, with this we will stop this video lecture. In the next lecture, which is the third part of puffs, we will look at how these puffs could be used to have an authentication without the need for any cryptography or secret keys. We will also see how there are several weaknesses which can occur due to this authentication scheme, and also ways to actually mitigate these potential problems. Thank you.